Good afternoon, everyone. My name is Marko Pakaslahti, and I'm coming from University of Oulu. My research focuses on integrated transceivers for observing the optical biosignals. And we have created a CMOS microchip, which combines the transmitter and the receiver first time in the world. And it's done by the L-Foundry 150 nanometer technology. The transmitter is a laser pulsar with adjustable pulse width, so that the current pulse is useful for different types of the laser diodes. And the receiver is a time-gated, time-resolved 4x8 SPAD matrix. In traditional measurement methods like continuous wave, only measures light intensity. And methods like this are analog, and any movement during the measurement creates an interference. Moreover, to measure like muscle oxygenation, we need data from deeper and deeper within the tissue, and the transmitter and the receiver distance have to be increased, which degrades the SNR. The time domain method introduces depth as a new dimension, and it's determined from the time of from the photons flight time. The measurement results can be obtained from the distribution time of light histogram, and the time domain approach allows us to keep the transmitter and the receiver as close as possible, which increase the SNR. Furthermore, the time gating increases the SNR and expands the dynamic range of the measurement because it allows the time window adjustment relation to the laser pulse, and with that the early photons of the Diode don't saturate the result. In this picture, we can see simplified block diagram of the transceiver. The reference clock is shared with all the delay lines against the PVT variations. And pulse width control is used to choose the width of the pulse, which is shared to the time gating process, which gets the SPADs loaded and start the time measurement in TDC. The same pulse is also going through the LD driver, which activate the current through the LD and emits the short laser pulse to the tissue. After that, the pulse scatters from the tissue, and the first SPAD that detects the photon sends the stop signal to the TDC, and the result is saved to the register. And after the predefined number of the measurements, the data from the register can be transferred to the FPGA. In traditional SPAD loading circuit, the SPAD anode is set to high with the quenching. And after the quench, the load transistor sets the anode to the 0. The loading signal have to be short, to prepare the SPAD to the Geiger mode as quickly as possible. And as the SPAD detects the photon, its breakdown voltage exceeds and causing the anode to go high. After the circuit is quenched again, the measurements cycles can start again. In our switched capacitor design, the quenching sets anode to a high and stop node to 0. After the quenching, the load signals open the transistor N1 and P2 so that the capacitor C1 can drain the charge from the anode. And this prepares the SPAD ready to detect the photon without the need of the lower the load signal. And this is why the Geiger mode is achieved in 150 under the 150 picoseconds. When SPAD detects the photon, the anode and stop signal goes high with the assistance of transistor P3. And after quenching, everything starts again. Here we can see 3 different test circuits. The test circuit A is used in all measurements, and there can be see also FPGA behind it. Its dimensions are 6 by 6 square centimeters, and the chip dimensions are 6 by 2.4 square millimeters. Circuit B features separate microcontroller circuit that makes the test circuit wireless. And in the circuit C, we can see the potential to reduce the size of the circuit. In the upper picture, we can notice the current pulses through the laser diode, and the adjustment is roughly 100 picoseconds. And the best tailored optical pulse we get with the shortest 835 picosecond current pulse. And that makes the optical laser pulse wide 111 picoseconds and approximate 1.5 watts. In this picture, we can see dark cut rate for the 27 SPADs. And it can be implied from the first 2 pins in the start that time required to load the SPADs in the Geiger mode have to be between 100 and 150 picoseconds. To resolve the average width of the pins, the laser pulse were emitted on the matte surface, which can be adjusted distance from the chip. And in this picture were sent 2 pulses, 2 measurements were made, and the distance was increased 5 centimeters. And calculation based on the weighted LSP suggests that the average width of the pin is about 52.5 picoseconds. The development of the time domain methods opens up various applications, including the measuring oxygenation from the brain and muscle during the exercise, and analyzing bone and fat tissues, and also aiding in cancer diagnostics. This method represents the next frontier for the consumer health electronics, and furthermore, its implementations in the medical devices has big potential to truly improve the speed, efficiency, and reduce the expenses in the global scale. Thank you for your attention, and is there any questions?